In this part, we are going to see several approaches to animate virtual characters. And first, we are going to see how we can deform the skin of a character given its internal skeleton. And then we will see how we actually articulate and generate the animation of the articulation of the character. So the most common approach to deform the surface of an articulated character is to use skeleton-based deformation, or also called skinning. So we want to deform a character that has articulation inside. And so the idea is to use a skeleton to model somehow the limbs of the character and that are going to undergo rotations around each articulation. So actually the animation skeleton is defined by a set of frames that we call TI, that are going to be 4x4 matrices containing position and orientation, and they are going to describe the non-rigid parts of the characters. So in other words, they are going to be the degrees of freedom of this character. So we are commonly calling join the frame of the articulation, and the segment between two joints is going to be called, obviously, a bone. So one can note that animation skeleton may be quite different sometimes from anatomical skeleton. Typically, we can see this example of cat in the bottom, where we've got a lot of bones that are defined in the head of the cats. And this is associated to the fact that the animator may actually be able to animate a lot of details in the head, such as the eyes, the ears, the nose, the mouth, and so on. So basically, for each of the elements that you may want to animate independently, you need a specific bones. As there is more details in the head than in the rest of the body, there is also more bones. The simplest approach to deform the surface is to attach rigidly a subset of vertices to a specific bone. And basically the vertices, they are going to follow rigidly the deformation which is applied to the associated frame. So for instance, in this case, there is the green vertex that are going to follow one bone, and the red vertex are going to follow rigidly another bone. So if you want to formulate the equation associated to rigid skinning, we are going to consider at initial state a frame T0 and its associated vertex V0, whose coordinates are V0. After deformation, we will have a new frame T that may be defined by a 4x4 matrix, or a translation and an orientation, and we are going to look for the 3D coordinates of the new vertex position V. So how can we express the vertex coordinate V with respect to the matrix T, T0, and the coordinates V0? One way to derive this relation is to say that the local coordinate of V0 with respect to the frame T0 is the same than the coordinate of the vertex V with respect to the frame T. So basically, the local coordinate of V with respect to T is T inverse times V, and it has to be equals to the local coordinate of V0 with respect to T0, meaning it's T0 inverse times V0. So at the end we can express V, and V is given as the product T times T0 inverse times V0. Or another way to derive this relation is to note that the deformation matrix M that deformed the frame T0 to the frame T is expressed by T times T0 inverse, and then we need to apply M to V0 to get the coordinate of V. Rigid skinning has the advantage to use this skeleton structure, which is very easy to build. And interacting with a skeleton is quite intuitive, actually, to model rigid articulation. But if we use directly rigid skinning, we will have discontinuities at the articulation and possibly intercollision of the mesh with itself. So to avoid these discontinuities and self-collision, we can use something called smooth skinning, where the idea is to actually blend the transformation around the articulations. So this smooth skinning is also called linear blend skinning, because we are going to linearly blend transformations. This is an example of a cylinder that is bent, and we are going to look at the position of the middle vertex between the two parts of the cylinder. If we were supposing that the point P0 were attached to the bone B1, then after deformation, we would get the position P with respect to B1. And on the other side, if we suppose that the point P0 is fully attached with respect to B2, like a rigid skinning, after deformation, we would get the position P with respect to B2. And basically the idea beside linear blend skinning is to say that we are going to linearly interpolate between these two positions, P with respect to B1 and P with respect to B2. As this position is really between the two parts of the cylinder, we can say that we take the in-between position, like half P with respect to B1 plus half P with respect to B2. If we extend the expression of P with respect to B1 with the matrices and P with respect to B2 with its own matrix, then we can see that at the end, the position P is given by a linear blending between the matrices, the matrix of transformation that are applied to the position P0. So this formulation can be generalized to arbitrary interpolation between two bones with different type of weights. Of course, if you are not in the middle between the two segments, but if you are more at the top of the cylinder, we may have a greater weight with respect to the bone B2. And if you are in the bottom of the cylinder, we may be related with a greater weight with respect to the bone B1. So in general, we can say that P is equals to alpha times P with respect to B1 plus 1 minus alpha P with respect to B2, or I can express it with the transformation matrix associated to the bone 1 and bone 2. And alpha is called the skinning weights. And if we now consider a generic shape that can contain any number of bones, not only two bones, then we can even generalize it to an arbitrary number of n bones, and we can say that P is equals to the summation of all the bones of the associated skinning weights, alpha k, times the position given by a given bones, or in other words, the summation of alpha k times the matrix of transformation mk, and everything is applied to the position P0. And to get correct result, we also need to make sure that if we sum all the skinning weights associated to a given vertex, then they all sum up to 1. So as a summary, smooth skinning can be seen as a barycentric blending of transformation matrix that we apply to a position P0. And this smooth skinning is actually the current standard for almost all articulated character deformation. It's used in almost all character in video games or animation cinema, for instance. So the advantage of smooth skinning is to allow quite an intuitive deformation through the use of the skeleton. The shape, the resulting shape can be controlled via the skinning weights. And the main advantage of this smooth skinning is that it's really fast to compute because it's basically a linear blending of matrix and then a product between a matrix and a vector. We can compute that on the GPU to have a real-time deformation. And this is the reason why it's so heavily used in animation, cinema, and video games. So I explained that for smooth skinning, we need skinning weights. So how can we generate skinning weights? Basically, currently, all 3D modelers propose interface to directly paint skinning weights on top of surface. It's not trivial to paint because it's a barycentric weights, meaning that if you increase the weights with respect to one bones, the weights with respect to the other bones are going to decrease. Otherwise, there is some possibility to compute automatically the weights, typically in using the distances between the vertex and the bones. The simplest way is to use Cartesian distance, where we compute the distance between a weight and each bones, and then we take the inverse of the distances that we normalize. But if we use Cartesian distance, we are not taking into account the shape of the surface, so we may consider incorrect distances between different limbs. So we can also use more advanced approach, like using diffusion over the volume or the surface of the mesh. And this process of defining skinning weights or painting the weights over the surface and more generally generating a relation between the vertices and the controller is called the action of ringing in production. So we saw previously that there is some standard format to store static shape, such as OBJ. Unfortunately, there is very few standard, especially open standard, to store animation and skinning animation data. So most common software such as 3D Studio, Blender, FBX and so on use binary file formats that may be difficult to parse, but we can still note the format Collada, which is an XML format that stores the data in ASCII. Or there is other format using JSON structure, for instance, like GLTF. But anyway, at the end, this type of file format, they are always more complex to parse and analyze, and they contain a lot of information compared to standard static mesh files. So they are more difficult to find and more difficult to handle. Also, linear blend skinning is associated to well-known limitation. So we already discussed the fact that setting the skinning weights may not be so easy. And also, linear blend skinning is associated to geometrical artifacts when we use large rotation. Two of them are named. The first one is the candy wrapper effect. If we twist a limb at 180 degrees, then the geometry of the shape is going to converge toward a single point. And this gives this kind of shape of candy paper. And the other one is called the collapsing elbow effect, which is associated to a local loss of volume at the articulation of the joint when we bend it using a large angle. And these artifacts are coming from the fact that we are actually linearly blending rigid transformation matrices. So if we want to avoid these issues, we should use some nonlinear blending. There exist some methods, such as dual quaternion skinning, that avoid these artifacts.